Okay, so first we'll talk about kinematics. And so I'm going to draw as best I can here. I'm going to draw a circular rod. We're going to keep our discussion to circular sections. And the reason for doing that is a couple of things are true, and I'll write them here. So we're going to have some assumptions about the way this deforms. It turns out that ends up being a good assumption for a circle. And the assumption really is that the planes, so if we take a series of cross sections through our rod here, so these would be cross sections. So these planes remain plane. So we don't have any warping. The other thing that happens is we don't have any change, no change in size. That's an in size. So if our circle starts out at that size, it doesn't get smaller as we deform it in torsion. And again, those are pretty good assumptions for a circle. So what does this look like? I'll grab a blue pen here. So what we're going to talk about is we're going to fix one end of this. So let's fix this guy down. We're going to have a axis here. So this is going to be X. And we're going to come into here, and we're going to apply some torque. So something like that. And we're going to start off, oh, geez. Okay. We are going to have some lines, and they're going to start off parallel with our rod. I'm going to draw a second rod now in the deformed configuration. See if I can do this. And here's our axis again. We're going to have this still be fixed to the wall. But now, instead of having lines that are, I guess I should finish this drawing first. Let's draw our sections. So we said our sections are going to remain plane. So we're still going to have those same lines. Nothing's going to change about them. So we'll draw those on first, because nothing changes there. But what is going to happen is if we turn this guy, so we're rotating, we're going to still use our right-hand rule to determine a positive rotation. And so if we rotate it in that direction, we're going to have the circle on this side rotate some amount, and we should get some lines that instead look something like this. And maybe I could draw one more that's rotated around from the other side. So in doing this, we have, there's our rotation. We've taken our lines and we've angled them. So we've changed the rotation of our circle. And when I wanted to kind of demonstrate what this looks like, you can sort of see this. This is not a circle, so what we're going to end up seeing is some warping. But what I could do is take this little girder section here, and I could twist on it. And so you can see, because it's an I section, you can see the twist now, right? So that's all we're doing here. We're going to twist the end of it, holding the other side fixed. And what we're looking at is we're looking at lines on the side of this. If we were to look at the end in cross-section, I'll draw a couple of circles here. My best here. and we were to draw a line from the center, we'll draw that as a point here. So that's our x-axis. We'll draw a line in some direction. We could locate some point, and we could say that that point is a distance rho away from the axis. So that's our definition of rho. It's just a distance away from the central axis, in this case the one defined by x. And we're going to be rotating this around positive, should be our right hand rule. If we go to our after picture, which is what I was trying to draw down here, we would find that our line, which was right here, has now rotated some amount. And if we wanted to measure that, we would use the symbol phi. So that's going to be the angular change from where it started as a function of x. And if we were to go out to our point P would have moved, and this would be our new point, P prime. It would still be a distance rho from the origin, or sorry, from our central axis, but now it's rotated some amount phi. And we can look at one of these elements here, and we can try to start to figure out how we can relate this angle phi to the amount of shear that we put into our material. So torsion, as it turns out, ends up just being a purely shear deformation. And that's what you'll see in this next picture. Where did my black pen go? So let's take this element right here, and let's move that down to here. And we're going to put it in as a light green square to start off with. So I'm going to flatten it out. And here is my square. And of course, my square has some dimensions. The dimension along the x-axis I'm going to call delta x. After we rotate our cylinder some amount, our square here is going to deform into some sort of parallelogram, and it's going to move down perhaps. And so now I'm going to draw that in my dark green, and I'll try and draw it as parallel as I can. And so now we want to figure out the distance from here to there. Well, we have an angular change, right? That's going to be our phi. And we have some relationship from our axis. We called that rho. And if I want to know how far a point on the outside of my cylinder, or anywhere on my cylinder here, moves, I would start there, and I would end there. And the distance from there to there is just going to be rho, which is our distance from our central axis times our angle. And we could think about that using our wooden blocks again. So I started off, here's my central axis here, here's my point, and that's going to be this side of our square. I'm going to rotate some distance. Let's see if I can get that. I'm going to rotate some distance phi, and now I need to know the distance between these 2 points. So all I have to do is take the leg of my triangle, say that that's rho times our small angle here, which we said was phi, and this distance is just going to be rho times the angle phi. So all I need to do is take rho, which is my measure from the central axis times phi at the value x. On this other side, of course, it's going to be, again, rho. Still, we're at the same distance away from our central axis, but now we have a little bit more or less phi, so that would be our rotation, and I would designate that with a x plus delta x. And we have seen a square like this before, right, when we were looking at our constitutive relationships. And what we said was that if I take a square and I shear it, that the way that we measure how much we've sheared it is actually this angle here. So that angle, we said, was gamma. So now what I want to do is try and relate these values to gamma, because that's what I'm really after at the end, right? We're doing kinematics, so we're trying to relate strains to displacements. And how would I do that? Well, I'm going to get the, this is the angle here, which is going to be the difference in my distances over delta x. As long as we're in small strains, this is going to be the larger one, which is rho phi x plus delta x minus rho phi at x. All of that over the distance between them, which would be delta x. You can see what we're after here. We're going to take the limit of this whole thing as delta x approaches 0. And you're going to get that gamma, which is our shear strain, is equal to rho times d phi dx. And that is going to be our kinematic relationship for torsion. We have a strain here. We have a distance from our central axis, rho. And we have some change in the angle. And so if you think about the units on this, strain, remember, is unitless. Rho has some distance. And d phi, so phi is an angle again, so it doesn't have any units. It's a radians, right, which are kind of like ghosts. And we're dividing that by the distance, x. So this is really radians per distance. So we have distance times radians per distance. That ends up being radians, and that works out for our shear strain. So the units are good there. And the only key that we want to point out here is that our assumptions that our cross sections remain plane, we don't get any warping, and we don't have any change in the size of our cross sections. That's good for circular sections. So our assumptions are good for circular sections. And if you have a general cross section, they will warp out of plane. And if we go back to my little bridge girder here, you can see that's quite evident. As I rotate the top, this corner here comes up out of the page. This corner here goes down into the page. And that's what the warping part is. So if we, for circles, this cross section is going to remain a cross section that's going to stay flat. As soon as I start with having more general shapes like this, now when I twist it, we're going to end up having some warping of the cross section.